Alright, so we're still talking about the damped harmonic oscillator, and first we're going to look at the case where there's two complex roots to the characteristic equation, and that's going to result in an underdamped situation, which means not too much damping. How do we get complex roots? We need the thing under the square root to be negative. So we set this to be less than 0, and then all of these constants are positive, so we don't need to worry about signs or absolute value when we take radicals. So we have gamma over 2m less than or equal to the root of k over m, which remember that used to be omega naught. So this means the damping constant, which just tells you how much damping there is, has to be some multiple less than the frequency. This over 2m was the frequency before. Okay, and we're gonna make things a little bit nicer. We're going to let mu. I just don't want to write out all that stuff, so I'm going to let mu be root of k over m minus gamma over 2m squared. This is the negative of this, right? We take out a negative sign, we get that. So that just means r is negative gamma over 2m plus or minus mu times I. Okay, that just means I have a little bit less writing when I write my solutions. So y is, remember we take e to the real part of this times t, and then we're going to multiply by c1 cosine, the imaginary part is mu t, plus c2 sine of mu t. And then we can do the same trick we did before with the undamped harmonic oscillator, and we can write this as a single sine or cosine. We're going to do cosine to be consistent with your Webasine and the other notation in this course. Mu t minus delta. And then, so what do we have? We have the same graph as before, some sort of cosine function, but now multiplied by a negative exponential. And you'll probably see it written like this, so I'm just going to write it like this, but that doesn't matter. Cosine mu t minus delta. Okay, so what does a negative exponential look like? Exponentials go this way, negative exponentials go this way. E to the 0 is 1. This does have an asymptote at the x-axis, or the t-axis, I guess in this case. E to the 0 is 1, so this value is c. And then natively, the cosine function looks something like this. Could be stretched or shrunken. Okay, so what happens? Well, we're going to multiply by whatever value is up here, this value. So we'll take that as the negative exponential. We'll multiply 1 by c, will be here. The stuff over here is going to be multiplied by something greater than 1, so we'll actually come up a little bit. It's going to be tangent to this curve. So the peak is not where the initial peak was. That's okay. And then we're going to multiply by smaller and smaller values. Like by the time we get here, we're multiplying this 1 by this value. And again, it's not the highest point. We got a little bit of a thing going up here because these values are higher than this value on the exponential curve. So what happens is we're now damped. So you get this function, and actually we could draw, you can draw symmetrically. So this curve is y equals c e to the negative gamma over 2 mt. This curve is going to be y equals negative c to the c times e to the negative gamma over 2 mt. This curve down here. And actually we should be bounded by both, so draw it like this. And we're going to be always tangent to both of these curves. The peaks will be shifted a little bit. It is tangent, it never crosses the curve. And then let's look at what happens. So now my period, they actually call it a quasi-period. Why quasi? Because it's still oscillating, but by the time we oscillate back, we're not at the same value, so it's not truly a period. The function isn't repeating itself identically. The period is now 2 pi over mu instead of, no, 2 pi over mu. Is this what I want? When I had a 4 pi in front of cosine, the period was 1/2. So yeah, 2 pi over mu. Okay. See, I don't have these memorized. I have to think about it. So quasi-period is 2 pi over mu, and notice mu was equal to the root of k over m minus gamma over 2m squared, which is less than, since this part is positive, it's something squared, less than the root of k over m, which was originally omega naught, we said. So mu smaller than omega naught, we're dividing by mu, so the period is longer than before. The damping causes the oscillations to slow, and it causes them to shrink.